So the last topic for our course is just a brief overview of organic chemistry. And so either this will be a good preview, so you'll be ready if you're going to take this class next semester, or it'll be just a quick look at what's going on with organic chemistry to give you a general idea of the kinds of topics that are covered there. So we'll start with a short Lewis structure review. So we'll just draw maybe 4 Lewis structures to remind us a little bit about what's going on there. So we'll draw CH4, NH3, H2O, and HF. So with CH4, that should be 8 valence electrons, 4 from the carbon, 4 from the 4 electrons, and we end up with this Lewis structure here. And so what we expect for carbon is that the valence is 4, and the way that's achieved is with 4 bonds and 0 lone pairs. When we draw NH3, that's also 8 valence electrons, 5 from the nitrogen, 3 from the 3 hydrogens, and we end up using 6 of the electrons to connect the 3 hydrogens to the nitrogen, and the remaining 2 as a lone pair. So now nitrogen, with its valence of 5, the typical arrangement for nitrogen is going to be 3 bonds and 1 lone pair. So you may remember something called the never over 4 rule, and the never over 4 rule tells us that we're never going to have more than 4 electron pairs around nitrogen, oxygen, or fluorine. And the explanation for that is just that these guys only have 4 orbitals, so they can only store electrons in 4 locations. So that's how we end up with the 3 bonds and 1 lone pair arrangement in NH3. We can see the same sort of thing happen for water and HF, hydrofluoric acid. So once again, for water, there are 8 valence electrons, now 6 from oxygen and 2 from the hydrogens. So a reasonable Lewis structure drawing looks like this. And now what we see from the oxygen is its valence of 6, and now that's achieved with 2 bonds and 2 lone pairs. So with the restriction of only 4 electron pairs, the only way I can reach a valence of 6 is with 2 bonds and 2 lone pairs. And then the last one that we can use to kind of finish out this row is HF, hydrofluoric acid. So now that's 1 valence electron from the hydrogen and 7 valence electrons from the fluorine to give us this Lewis structure. So then here we'd say for fluorine, with its valence of 7, our expectation is what it's typically going to do is make 1 bond and have 3 lone pairs. So we've looked at the bonding we expect for carbon, hydrogen, nitrogen, oxygen, fluorine, and fluorine is kind of representative of the typical patterns we expect from the other halogens like chlorine, bromine, iodine. So the general understanding of how the Lewis structures work for these atoms should be enough to talk about most of what we want to with regard to organic chemistry. So the next thing that I want to talk about is the first family of compounds we usually consider in organic chemistry, and these are the hydrocarbons. So like the name suggests, these are molecules that contain only carbon and hydrogen. And the first group that we can talk about are what are called the alkanes. And in the alkanes, we're only going to have single bonds, whether that's between carbon and carbon or carbon and hydrogen. Everything will be a single bond. And these guys all have the general formula CnH2n plus 2. So I can just plug in anything for n, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And if I follow that formula, that'll give me the formula for an alkane. So we just saw one of these, right? CH4 is the first one we drew, and that is named methane. So this meth prefix means one carbon. And we know when we draw this Lewis structure, it's just 4 hydrogens attached to one carbon. And this is for n equals 1, right? That would be C1H4. We can keep going from there. We could have C2H6, and that's called ethane. And now here, this F prefix is to indicate a 2-carbon chain. And so now that means my 2 carbons are connected to each other. And then remember, I'm trying to satisfy their valence of 4 total, so they each get 3 hydrogens in order to achieve that. And so technically this would be where n equals 2. Okay, we'll do 2 more of these, and then I'll just show you the names for the rest of them once you start to get the pattern here. So then we can go to C3H8. That's called propane. And here, this prop prefix means that it's a 3-carbon chain. So now, I'll connect my 3 carbons in a row. So the outer carbons each need 3 additional groups attached. So we can do that. 1, 2, 3. On the other side, 1, 2, 3. But the inside carbon was already attached to 2 carbons, so it only needs 2 more hydrogens in order to reach its valence. So this may start to show you what the N pattern is in terms of CnH2n plus 2. The outer carbons are always going to need 3 hydrogens, but the inner carbons are only going to need 2 hydrogens. So the CnH2n plus 2 is to say every interior carbon needs 2 hydrogens, so the 2n, but the 2 n groups are each going to need 1 more, so that's how we get CnH2n plus 2. Okay, let me draw the C4H10 structure, and then I'll just name the rest of them up to 12. So C4H10, that's called butane, and that but prefix is what we expect whenever it involves 4 carbons. So same sort of pattern here, right? I'll connect my 4 carbons in a row, and now, let me fill in my hydrogens first. The outer guys are each going to get 3 hydrogens. And then the inner group, since they already have 2 attachments, they only need 2 more hydrogens. And that gives me the structure C4H10, and that's for n equals 4. All right, so that should be enough to give you an idea of the overall pattern, and we'll revisit this in more detail in just a little bit here. Let me name the rest of them for you with the formulas, and then we'll talk about a shorthand drawing method for all of this. So if we're following the plan, it would be C5H12, C6H14, C7H16, and C8H18. So that's CnH2n plus 2 for all of those. And then we can give these guys all names. So this is pentane, hexane. This is heptane. And then octane. So you're getting these standardized prefixes for all of these that tell me the carbon count. Okay, we can keep going a little bit more. If it were C9, it would be H20, C10, H22, C11, H24, and then C12, H26. So now we've got nonane, decane, undecane, and dodecane. So that's usually about as far as we go when we're counting these off, up to 12 to kind of show all the variations. You can see they're pretty much following the prefixes like they would for polygons. It's just the kind of standardized prefixes. So you can imagine if I had to draw C9H20, it would be a lot of work to draw in all of those carbons and hydrogens. So for that reason, we're going to introduce something called line angle notation. And line angle notation will make life substantially easier once we make sense of it. So let me draw out some more of our Lewis structure format and then show you the corresponding line angle, and hopefully that'll help make sense of what's going on. So C3H8 we drew earlier, right? Just 3 carbons in a row, and then I filled in my hydrogens around those. And we know our molecule here contains 3 carbons. In the line angle notation, I really end up drawing zigzag lines to indicate a carbon chain, and that's sort of representative of how things would look in terms of the structure. So that is the shorthand way of drawing C3H8. So the end points of the line each represent a carbon, and any vertex where the 2 lines meet also represent a carbon. So the key idea here is that the H atoms are implied. So I don't need to fill in all of my H's. We just assume each carbon has the appropriate number of hydrogens in order to reach its valence. So when you think about what I've drawn here, what I'm really saying, this would defeat the purpose of line angle, but at least you can see what I mean. What I'm really saying is there are 2 hydrogens on the interior carbon, 3 hydrogens on each of the outer carbons. So that's what I mean when I'm saying that they're implied. And then again, that's carbon 1, carbon 2, carbon 3, like that. So we can kind of keep following this plan to draw the rest of them. So C4H10, I'll draw the Lewis structure one more time, and then I think after that, hopefully it'll make okay sense. So 1, 2, 3, 4. So 2 hydrogens each for the interior carbons, and then 3 hydrogens on each of the end carbons. So even at that point, right, we're getting kind of tired of drawing our Lewis structures out, so then quite simply we can just draw this line angle structure. And again, just for clarity, this is 1, 2, 3, 4, 1, 2, 3, 4. Okay, for the next 2, I'm just going to go straight to the line angle drawing, and hopefully that makes okay sense. So C5H12 would just look like this, 2, 3, 4, 5. So that first pen stroke counts as 2 carbons, right? Because I'm really drawing the line between carbon 1 and carbon 2. And then each one I draw after that, I'm adding 1 more carbon to the chain. And then C6H14, now it would be 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So that's a really important thing to think about as you're drawing these. Just consider that first pen stroke or whatever is counting for 2 carbons, and then I go on from there. A lot of people in the beginning accidentally draw 1 carbon too many just because they forget that first line really represents 2 carbons. So one of the ideas we can think about with all of this is the concept of constitutional isomers. So we talked about a variety of isomers in the coordination compound section, but constitutional isomers are more typically discussed in organic chemistry, although we still have them in coordination compounds. So when we talk about constitutional isomers, these are molecules with the same formula, but a different connectivity. And that just means the atoms are attached to each other differently. So, for example, with C4H10, I could draw this with 4 carbons in a row, 2, 3, 4. That would be one way to draw C4H10, but there's another way I could draw it as well. So kind of my last round of drawing Lewis structures here, and then we'll go exclusively to line angle for a little bit. So C4H10, that's one way for me to draw it. But I could also imagine a structure where it's 3 carbons in a row, and it just happens that the second carbon has a carbon attached to it. That's the only other arrangement of 4 carbons and 10 hydrogens that I can have. The way this is set up, we've really got 3 outer groups that each get a CH3. The inner group only needs 1 more group, so it gets a hydrogen. And then this outer group, I didn't really leave myself enough space here, would also get 3 hydrogens. So how would that look in line angle? Well, here's 3 in a row, and then off the central carbon, there's a group going up. So here are our carbons, 1, 2, 3, 4, and then here, 1, 2, 3, 4. So when you look at carbon 2, it's kind of like an arrowhead pointing up. So then when I want to draw a group coming off of that carbon 2, whichever way the zigzag points, whether it's an arrow upward or downward, if I'm extending 1 or 2 groups off of that carbon, it needs to go in the same direction as the arrowhead. So I couldn't point it downward. Anyway, those are 2 constitutional isomers for C4H10. We can do the same thing for C5H12. And so I'll do this all in line angle. So one version would be all 5 in a row. So 2, 3, 4, 5. I could also have 4 in a row. 2, 3, 4. And then in that case, I could have my branch coming off of carbon 2 or carbon 3. Keep in mind, this drawing is the same as this drawing. So if I could draw something that I think looks different, but I can rotate it to be exactly aligned the same way, then they're not different. So the third option for C5H12, if we want to think about what to do here, it will be 3 carbons in a row. Let me draw that again, that wasn't so great. 3 carbons in a row, and then 2 branches coming off of that. So let's draw that one as a Lewis structure just to be clear. So there's a central carbon, and then coming off of that carbon are 4 other carbons. So the inner carbon doesn't need any hydrogens, but the outer 3 all need 3 each. So just to be clear that we're still achieving our formula of C5H12. So hopefully line angle is making sense and the concept of constitutional isomers is starting to make more sense. We'll do C6H14 and then we can work through C7H16 as well. So C6H14. So here you could imagine 6 in a row. So 2, 3, 4, 5, 6. 5 in a row, 2, 3, 4, 5, with a branch on carbon 2. And then we could also have 5 in a row with a branch on carbon 3. So these are not the same, right? Then we could go to 4 carbon branches, 2, 3, 4, and now I could either have groups together like that, or groups apart like that. So again, seeing my main carbon chain, 2, 3, 4, 2, 3, 4. So those are the 5 different constitutional isomers that we can have with the formula C6H14. So in the handout that I'm more or less following at this point, I just asked to draw all of the constitutional isomers you can think of for C7H16. So if this is making sense and you want to give yourself some practice to see if you're doing okay with this, pause the video and give it a try to see if you can draw all the combinations of C7H16, and then I'll show you all of my answers. So strategically, if you go back to look at what I did for C6H14, I'm grouping them, right? My first row was all the options with a 6 carbon chain, then a 5 carbon chain, and then a 4 carbon chain. So that general strategy should work fairly well when I try to do the same thing for C7H16. So let's try that. So for 7 in a row, right, it's pretty clear. I just draw 7 carbons together. 2, 3, 4, 5, 6, 7. And then for 6 in a row, 2, 3, 4, 5, 6, and my branch could be on carbon 2. Then I could also do the same thing, but with my branch on carbon 3. 2, 3, 4, 5, 6, like that. 1, 2, 3, 4, 5, 6. So if I put the branch on carbon 4, it would be the same as putting the branch on carbon 3. If I put the branch on carbon 5, it would be the same as putting the branch on carbon 2. So those are all my options for a 6 carbon chain. So then how about for 5? 2, 3, 4, 5. So if kind of following the example from above, we could do 2 together. And we could do that on carbon 2 or carbon 3. But we could also do 2 apart. So we could do 1 on carbon 2 and 1 on carbon 3. We could do 1 on carbon 2 and 1 on carbon 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then there's one more option for 5 carbons, and that's where I have a 2 carbon fragment coming off of carbon 3. So usually this is the one that people miss, especially as you're just getting used to this idea. But this one works because it's still a 5 carbon chain no matter how I count it, and there's just a 2 carbon branch off of carbon 3. So even if I labeled it differently, I'd still have a 2 carbon branch off the 3rd carbon of a 5 carbon chain. All right, let me sneak in the last one here. There is a 4-carbon option. So if I draw my 4 carbons out of my 7, I know there are 3 others that I can attach. If I add them to carbon 1 or carbon 4, all I'm going to do is make a 5-carbon chain. But if I add 2 of them to carbon 2 and 1 of them to carbon 3, that would be my last option. So I think there's supposed to be 9 of these. Looks like we did it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's the general idea that we're thinking about when we're looking at constitutional isomers. So I think I'll cut this recording off just so we have one single recording just to this point,